In this video, we're going to look at the question of when are two left cosets equal. Now to start with, I want to do a little bit of review. The first thing that I want to do is I want to recall that the definition of a left coset involves the following kind of thing. We need to have a subgroup of a group G, and we need a fixed element named G inside capital G, and the left coset, which is written GH, is nothing more than the set of objects that look like G times little h, where little h is running through all of the elements in capital H. Now, we have previously seen that if I look at two elements, G1 and G2 inside G, then it turns out that either their left cosets are equal to each other or their left cosets are disjoint. And what this fact says is that the set of left cosets of a subgroup H partition the group G. And we can kind of pictorially think about what that means by kind of thinking along these lines. If I just have a great big glob for G, and I put H over here, it's important to remember that the left coset EH is just H, where E is my group identity element, because the group identity of any group has to be inside all of its subgroups. So this is EH, and I'm going to have some subgroup that I'll call G2H, and then I might have another left coset G3H, and another one, say G4H, and so on. I might have an infinite number of these cosets if G itself is infinite. If G is finite, then Lagrange's theorem is going to give us a very nice relationship between the number of cosets and the size of the group and the size of the coset. We'll look at that in a different video. It's not important in answering our particular question. But what I do want to notice is that G is the union of all of the distinct left cosets of H. And it would be really nice to be able to tell when two cosets are equal to each other. Now, one thing that I also want to do is establish a piece of notation. Let's just go to the next slide. So if we have a typical left coset GH, we call G a representative of that particular left coset. Now, what we have to investigate is this idea. If I happen to have a coset AH, so that's my representative, and I happen to have a coset BH, so B is my representative, and if they happen to be exactly the same coset, then I'd like to know what happens. What kind of relationship can I say that I have to have between these two representatives? Well, we can get at that by actually examining some important ideas. So what I'm going to notice is this sort of a thing. We know that A is equal to AE, and E is inside of the subgroup H, so A will always be inside the left coset AH. Likewise, B is equal to BE, and that E is inside our subgroup H, so B will always be an element of the left coset BH. Now, if AH and BH are the same left coset, then what that says is that A belongs to the coset BH. And so what that means is that A is equal to B times something inside H. So for some H inside H. Now what I want to notice is that I can take this particular inequality, this particular equation, and I'm going to pre-multiply it by B inverse. And when I do, I get this lovely little fact right there, and that's going to say that what we're looking at is B inverse times A is equal to EH, and that's just H. And that says B inverse times A belongs to the subgroup H. So what we've done is that we have actually proven the following proposition. So we have proved the following fact. And let's get this fact written as a proposition. Let H be a subgroup of G if left coset AH equals left coset BH, then we know B inverse A belongs to H. Now I'm actually going to add here that we also know A inverse B belongs to H. And the reason that we know that is the following. Let's go back to this color. If I look at B inverse A's inverse, that turns out to be A inverse B. And since H is a subgroup and this guy is in H, H is a subgroup forces its inverse to be in H. So A inverse times B is also in H. Now what this proposition that's in this kind of greenish color is really saying is that if I happen to have two cosets that are equal, then I know that if I take one of them's inverse and multiply it by the other guy, so A inverse times B, or this guy's inverse times that guy, that would be this thing. No matter which way I do it, I'm going to get an element in H. It is important to notice that the inverse is always on the first of the two pairs of elements for this guy. Well, that tells us that if we know two left cosets are equal, then we know something about the product of one of them's inverse times the other one. That weird product is going to be in H. Well, now that we have this proposition proved, let's ask the question, can we prove its converse? So let's look at the converse of this particular proposition. Well, so the converse would state, if this funny product, A inverse times B, belongs to H, then the two left cosets are equal to each other. So let's see if we can get this thing proved. Well, there's our hypothesis. Since A inverse B belongs to H, we can write that A inverse B is equal to some H inside capital H. And now what I want to notice is that we can pre-multiply this particular equation. We're going to pre-multiply that equation by A, and when we pre-multiply it by A, we're going to get A times A inverse times B is equal to A times H. Well, we can slap those parentheses around that, and so what we now have is E times B is equal to AH, where that little h is inside capital H, and EB, of course, is just B, so B is equal to little a times little h, and that says B is an element of the left coset AH. And so what this says is that and now what I want to do is I want to use this fact to show that, this says that the intersection between the left coset BH and the left coset AH is not empty because B belongs to both of them. We know that B belongs to BH, and we know that B belongs to AH, so that intersection is not empty. And the fact that that intersection is not empty is enough to say that the two left cosets are indeed equal to each other. So what the upshot of this is that we now have an if and only if theorem that I want to state very carefully. And so our theorem is going to say this. Let H be a subgroup of G, and A and B are any elements of capital G. Then we have the two left cosets, AH and BH, are equal to each other if and only if the weird product A inverse B belongs to H, or if you would prefer, B inverse A belongs to H. Because remember that A inverse B's inverse is just B inverse A. So these two things either both belong to H or they both don't belong to H. So if one of them belongs to H, they have to both belong to H. So let's just skip a little or in there. And so what this basically gives us is a specific test for when two cosets are equal to each other. The product of the inverse of one of the representatives times the other representative has to be inside the subgroup. Now, this basically means that if we have a finite situation, so if my subgroup H happens to have L elements, and we can write H then as E will be my first element, and H2 will be the second one, and H3 will be the third one, and HL will be the last one, then what it means is that if I look at AH, that would be AH2, AH3, all the way up to AHL. Any one of these guys can be thought of as the representative, So any one of these is a representative of the left coset. So if we have AH is equal to BH, what that basically means is that B is one of these guys. And so if we actually start writing out the specific elements of a left coset, it doesn't matter which one we pick for the representative. And that should be enough for this particular video.